Okay, so let's start the talk. This week we have David Carchedi giving us the talk on, I think, derived differential geometry and quantum field theory. Okay, so
thank you very much for the invitation. Okay, so I'm going to start by kind of telling you what like differential geometry is, derived differential geometry is supposed to be about, and then we'll get into the field theory aspects. So at the core is the concept of transversality. Is this readable, or is it still grainy?
Yeah, that's readable.
Perfect. Okay. All right. So just to remind you, what it means to be transverse. If you have smooth maps, say F and G, from two different manifolds to another manifold, and you can look at the points of M and L, which get mapped to the same point in N. And you can say that F is transverse to G if at all such pairs of points, the sum of the images of the tangent spaces together generate the tangent space of the image. So a simple enough definition. In particular, if one of those manifolds, M or L, was a point, then that would be asking for the other map to be a submersion. So, and what's good about transversality is if you have transversality, well, then the pairs of these points, this fibered product, actually is a categorical fibered product and is a closed submanifold of the product. So you construct new manifolds by taking fibered products of transverse maps. But what about without transversality? Well, then it can be quite far from being a manifold. And I mean, it can fail to extreme levels. So as I mentioned, if you have one of those maps being a point, let's say that it's mapping just the origin of R into R. This is going to be transverse if and only if it's a submersion. So level sets of a submersion give you manifolds, but every closed manifold of any closed subset of any manifold is a zero set of some smooth function. So if you didn't ask for transversality, you could just get any closed set at all. You can get stuff that's like, you get literally the Cantor set, or you can get things that like behave like their Cantor sets, so things that are very different than manifolds. So I mean, it can fail as wildly as you can imagine. So this isn't so good. Okay, so now this can cause some problems because.
Sorry, can I ask a question, David? This might be a really dumb question, but what's the closed?
Absolutely.
What's the smooth function which gives you the Cantor set as a zero set?
Oh well, so in general, there's a theorem of Braille that that says that any well, there's two ways of saying it. Yeah, well, I guess usually it says that you can. Okay, explicitly, you can try to smooth out the function which is the distance from the Cantor set.
Right. Okay.
And you can do this.
Sure.
Yeah, so that's like if you want to think about how to do it concretely. But yeah, I mean,
okay, but this
because
is just
you have
general
functions,
existence.
you can do it for anything.
Okay. Yeah. Awesome. Cool.
Yes. Exactly.
Thanks.
Yeah. No problem. So I mean, that's a good question. Because I mean, it's fairly counterintuitive. It's like, you know. Smooth geometry is great because you have predictions of unity, but it's also wacky because you have predictions of unity because they behave kind of counterintuitively, particularly if you think algebraically. Okay, so a very common way to produce moduli spaces is like a very common setup is you have some vector bundle over a manifold and you have some section, and you want to cut out the zeros of that section. This section might be describing some sort of equation that you want the solutions to. That'll be your moduli problem. And so you're looking at the intersection of the section with the zero section, or more precisely, it's a fibered product over the vector bundle with M. One map being the inclusion, which is the zero set, and the one is the inclusion, which is the section at hand. And so you can look at this this intersection. That's your moduli space. So it's a space of solutions to this equation. Often this can be sort of PDE that you're trying to study. And the problem is that if you don't have transversality, well, then this moduli space can be very singular because it's the same problem as before. I mean, you can basically get any closed subset that you want this way. So, and when it's not a manifold, you can't use the tools of differential geometry to study it. So, I mean, you can't really do much with it. And there's all sorts of, there are all sorts of methods to try to give some sort of smooth structure to this. There's a rich history there, but certainly it fails to be just a manifold. Okay, now there's a enhanced version of differential geometry which is designed precisely to deal with these kinds of issues. So it's called derived differential geometry. And I'm going to do a different approach than what's typically done when describing what derived differential geometry is. I'm going to start with what the universal property we want to be, and move up from there. So let's just think categorically for a second. So let's think about derived manifolds via some sort of universal property. Okay. So so there's a story which I don't have time to get fully into, but first of all, whatever derived manifolds are, so this is some sort of enlargement of the category of manifolds which has all the fiber products that you'd want, but they behave like the good fiber products from transverse ones in particular. If you have a transverse pullback of manifolds, it's still a transverse pullback of derived manifolds. So it's still a pullback of derived manifolds. But it turns out that to have this behave correctly with respect to cohomology, you need to have a higher category structure for derived manifolds. It can't just be a one category. The reason is, so if you look at, say, looking at a point intersecting itself inside of R, that's a point, but that's totally non-transverse. And that intersection will just keep happening in your category if you're in a one category. Because if you have a pullback where you have point, that's terminal objects, and then you have to be something that's just a subset of, or a sub-object of the terminal object, and then you're stuck. But for a higher category, we know this isn't the case. Like if you look at spaces, like the infinity category spaces, if you will. So just think about homotopy theory spaces. If you have point, you're going to get the loop space, right? And that's not contractible. So that gives you a way out. There's a whole story there, but that's the basic idea. So so we have this infinity category of derived manifolds. I didn't say what it is. I'm just saying, suppose there existed one, and roughly the idea is we want this universal property, but then I'll give you a slightly better one. But first of all, we want that the inclusion of manifolds into derived manifolds to preserve transverse pullbacks. So that's just saying that every time you have a pullback diagram of manifolds and the maps are transverse, that this remains a pullback when you look at it in the category of derived manifolds, or the infinity category of derived manifolds. And it should preserve the terminal object. That's just saying that if you have any derived manifold, there's a unique map to the point, which, I mean, that's a very reasonable geometric assumption. So now suppose that you have some functor out of the category of manifolds to some infinity category, and this functor, it preserves the transverse pullbacks and it preserves the terminal object. Then you want to extend to a unique functor out of derived manifolds which preserves all the finite limits. So that's some way of saying this, like the universal completion in respect to pullbacks that respects transverse pullbacks. Okay, and that's almost exactly what you need. There's just some technical details. So, and also this isn't really an infinity categorical statement to say that it exists unique. We should have some sort of homotopy statement. So here's how you can actually do it. And this is, so this definition is due to myself and Pella Steffens, but we got some motivation from paper of Andrew McPherson. So you just say that to derived manifolds is idempotent complete, and that part is and has finite limits. This is a strange thing if you don't know about infinity categories. Being idempotent complete is like if you have finite limits, you're idempotent complete if you're a category. But it turns out that the data of a retract being homotypic coherent to all orders is a non-finite limit if you're in an infinity category. So if you're an n category, for any n, it's a finite limit, but otherwise it keeps going. So small technicality. So you want to have, be able to split idempotents, and you want finite limits. And okay, we want there to be some functor from manifolds, derived manifolds, which preserves transverse pullbacks in the terminal object. You'd probably want to say, oh, I want this to be fully faithful, right? Like you want to think about manifolds as being a subcategory there. And well, this is true, but it turns out if you just ask for it to be some functor, it will turn out to be fully faithful if it satisfies the universal property I'm about to give. It's non-trivial, but it actually does happen. So what we want is that if I have any other infinity category, which you can split all the idempotents and it has finite limits, well, there's induced functor that you can get between functors from derived manifolds to that infinity category, which preserve finite limits, to functors from manifolds to C, which preserve transverse pullbacks and the terminal object. Because if I have this functor from manifold to derived manifolds, I can just compose it with the functor that I had from derived manifolds to C, and then I get a functor satisfying that it at least preserves the transverse pullbacks and the terminal object, right? And you want that this the functor induced by the functor I between the functor categories, so just by restricting, we want this to be an equivalence of infinity categories. So that's saying that this F exists uniquely up to homotopy. Okay, so is there questions about the universal property? No? Okay. So just by abstract nonsense, there exists such a thing. Like you can just, there's some machinery that you can just spit it in, like put it into, and it spits out, okay, there is some construction of this, but that's nice, but that's not very useful in the sense of like, what is it? Can you work with it? Like, this is not the approach I want to do. I don't want to say like, yeah, let's keep working with this definition. I want to start with this definition, and then I want to get something I can work with out of it. And this also, it pins down exactly what we mean by derived manifolds. So we don't have to say, okay, so-and-so has this definition, so-and-so has this definition, are they the same? Well, now we have a criteria to check, are they the same? Do they agree with this universal property? So it clears the air and says like, we know what derived manifolds is as an infinity category. Now we just have to find different descriptions of that. Great. So let's go and switch gears and talk about C infinity rings. Now, the reason is that, one reason is that every existing theory of derived differential geometry or derived manifolds, it starts with C infinity rings. And for a while, that was just kind of, it seemed that it was, it's just like the easiest thing to do maybe, but maybe it's not the only thing to do. But it turns out that the very concept of C infinity rings is intimately linked with the universal property of derived manifolds, which is pretty surprising, to be honest. Like when I figured out this was true, I was pretty like shocked. Like I didn't believe it at first. Pella had the idea that this should be true, and then I didn't believe him. And then like a couple months later, like a proof popped into my head of like why this is true, and I was like, whoa, that is weird. And then so anyways, it's counterintuitive, at least for me. But what is a C infinity ring? Let's just back up and say like, what are we talking about here? So it's basically a commutative R algebra, but some extra structure. Okay, like think about smooth functions on a manifold. It's a commutative ring, but there's some more structure there. So what kind of extra structure do we have? Well, in particular, if I have a smooth function from Rn to R, I get an n-area operation on my algebra induced by that function. And then they should be naturally compatible with respect to maps between Rn's, which are smooth. So what do I mean? Let's just look at that example I mentioned of, say, smooth functions on a manifold. Well, if I have n smooth functions, I can just pop them into the entries of another smooth function from Rn to R and get a new smooth function on M. And that's an operation which makes sense. It won't make sense for any arbitrary ring, but it makes sense for smooth functions on a manifold. And smooth functions on a manifold are the prototypical example, so to say, of a C-infinity ring. And C-infinity rings, the theory of them turns out to be, it's in some sense a mild extension of ordinary commutative algebra. In some senses, it's not mild, but if you can work with commutative algebras, a lot of the stuff carries over. The most important thing is if you have an ideal and you take the quotient ring, is automatically a C-infinity ring still. So this is really good because we don't have to invent some new notion of ideal, and you can just kind of do ordinary algebraic geometry, so to say, but you just work with max spec. If you take max spec of C-infinity M, so technically R spec, so you want to solve the prime ideals, all the maximal ideals of residue field R. This actually recovers the manifold. So if you have, this gives you an idea of spec. So now all of a sudden, manifolds are affine schemes. So that's interesting. Okay, so so C-infinity rings were initially developed to develop models for synthetic differential geometry. Derived differential geometry was not even in the wind, so to say. Okay, so let's just say more formally what a C-infinity ring is. So the actual definition is you, just for notation, to be kind of funny, you say that C-infinity is the subcategory of the category of manifolds on the Rns, okay? That way, it's just kind of a cheeky thing to do because if you think about this as a Levier theory, then it's a C-infinity algebra. So anyway, that's just because you're calling it C-infinity. But a C-infinity ring is just a finite product preserving functor from this category to sets. So that's, it's like, okay, what's that have to do with being a commutative ring? Well, I claim that if you look at where R is sent, then that set inherits the structure of a commutative ring. And the reason is R itself is a smooth ring. Like it's a ring which is a manifold at the same time. Namely, we have addition and multiplication, and those are smooth maps. And everything about, well, I guess I should also talk about the unit, but that's obviously smooth as well. And all the operations of a ring can be expressed as diagrams between the product of the underlying set with itself and using addition and multiplication. And since you preserve finite products, then you get those diagrams become maps between the products as before, so you get a commutative ring structure. But you have more information because we have to also have some sort of n-area operation for each smooth function. Okay, and just for peace of mind, so to say, or to understand that this is like really the natural thing to do, is instead of taking C-infinity, you pick some ring you like, say R, and then you looked at, say, commutative ring, and you looked at affine schemes over R. And then just looked at those of the form like a to the n for some n. So looking at the affine plane, and just looked at all the maps between those, and you ask for a finite product preserving functor to set. That's the same as commutative algebras over R. It turns out. I mean, one way is this, and so that gives you a functor, so to say, and turns that functor is equivalence. So it's a way of packaging what it means to be a commutative algebra, but now we replace, finite schemes by, affine schemes by smooth maps between Rns. So, are there any questions? Okay.
But sorry, but you are not saying that the C infinity ring is a algebra over C infinity of R.
No, it's an R algebra.
Mm-hmm.
It's an R algebra, but it has this extra structure. So like anytime you have a smooth map between RNs, you get this a map from say C infinity. You get if your C infinity ring is A and have a smooth map from Rn to Rm, I get a map from AN to AM, which is like functorial with respect to these maps. Okay. So you can actually make sense of this. Well, you can first ignore the infinity part. If I have any category, I can talk about a C infinity ring object in that category. As long as it has finite products, I can just say it's a finite product preserving functor into that category. If the category is sets, you get computed rings. But for instance, you could take, say, sheaves over some space, and then that would just be a sheaf of C infinity rings. But you could also make C be a higher category, and you can still ask for this to be a finite product preserving functor. And you can think about this as being a C infinity ring or a weak C infinity ring or a C infinity ring up to homotopy in your infinity category. The language of infinity categories allows you to just make the same definition. So you can look at the infinity category of the C infinity ring objects in your infinity category, which is just the subcategory of the functor category on those which preserve finite products. Okay. Now, if you're trying to talk about what a C infinity ring is up to homotopy, it would make sense to, instead of working with sets, work with spaces or infinity groupoids. Okay. So now, why would you want to do this? Well, let's say that you
just
had.
To clarify, when you say spaces,
yeah.
You mean the category of topological spaces as an infinity category, including homotopies, right?
Including homotopies, right? So that's why I put in parentheses infinity groupoids. So I don't mean like the one category of topological spaces. You could do that, but I mean it's not what I'm doing. I mean, if you do that, you get a topological C infinity ring, but I want a C infinity ring up to homotopy. So coherent, maybe it's better to say a homotopy coherent C infinity ring up to homotopy. So if you talk about, say, a commutative ring in spaces, then this is the same thing as a simplicial commutative ring. And if you're in quadratic 0, then that's going to be the same thing as a DG algebra. So this is a good reason to try to do this for the C infinity case. Okay, so we can take this infinity category, and by some just general theory, so if this done general in terms of model categories, is Julie Bergner. She just said this for Levier theories, and then there's also stuff in HTT on this. You can always model this as, so let's do this in the case of C infinity. So you can take simplicial C infinity rings, and there's a model structure. So I mean, you just want the fibrations of weak equivalence to be like those are the underlying simplicial set. And well, there's a canonical way to construct an infinity category from a model category. It's called taking the homocoherent nerve. So that's just like saying what the infinity category, this model category is representing. And it's equivalent to, well, the actual infinity category of algebras in the infinity category of spaces. Okay. So, so that means that simplicial C infinity rings is one presentation of this infinity category. Okay, but we're in characteristic 0. So, I mean, why don't we work with DG algebras? That would be a nicer thing to do. They're easier to work with. You know, we have homotopical algebra at our disposal. There's a model category due to myself and Dimitri Reudenberg on what we call differential graded C infinity rings. So our actual definition, we use ideas from supergeometry. like morphisms of the, and actions of the endomorphisms of the Euclid line. But it turns out that this is equivalent, and we showed this in our work as well, to a very simple description where you just have a commutative algebra. So you have a commutative differential graded algebra, but at the level of 0, so A0 is just an ordinary commutative algebra. We ask for that to have a C infinity structure. So it's not just a commutative algebra, but it's a C infinity ring. And then you want the maps between the differential graded algebras at level 0 to be a map of C infinity rings. So it has to respect these extra operations, okay? But otherwise, it's exactly the same as DG algebras. But what it does change is it changes the tensor product. So, and that's something I should have mentioned, I guess. So I can erase this after, but if I take, say, C infinity of M, and I tensor over R with, say, C infinity of N, that's not the same as C infinity of M cross N, right? I just get something which is like some sort of subset of that, right? Which is like polynomial in some sense. But this is not the coproduct. The tensor product of R is not the coproduct in C infinity algebras. There is a coproduct, and you can write it like this. And this is equivalent to this. So it's somehow like the C infinity completion of the ordinary tensor product. But it satisfies the uniform property of a coproduct, so it's the right thing. And if you're trying to solve fiber products, then in terms of algebra, you're trying to derive the tensor product. So, but we're deriving a good tensor product to start with. So this is it's kind of the right thing to do. And so our motivation came from trying to model derived manifolds with DG manifolds. So if I have a differential graded manifold, so that's a super manifold with some extra bells and whistles added to it. In particular, you have a differential, which is a degree 1 vector field, which graded commutes with itself. If you look at smooth functions on that DG manifold, it gives you a DG C infinity algebra. So just as the prototypical example of a C infinity ring with smooth functions on a manifold, the prototypical example of a DG C infinity ring is smooth functions on a DG manifold. So
Dave,
yep.
with the point where you can say that this abstract category of derived manifolds you defined originally using some universal property is equivalent to this category of DG C infinity rings, so that it's a nice presentation for it?
Well, it's almost true, and yeah, I'm just about to say something like that. Okay. So, yeah. Okay. So, but you're thinking exactly correctly. So, first of all, DG C infinity algebras gives you a different description of C infinity algebras and spaces. So this is, if you want, comparing this directly with simplicial, that would be a C infinity Dold-Kahn correspondence. So there's a monocategorical argument given by Roidenberg, but he never wrote it out as a paper or anything. And then there's in Joost Nouden's thesis, he does his own proof using infinity categories, which is now out. So so it's nonetheless true. So these are all describing the same thing, which you can just call, say, homotopical C infinity rings. Okay. So here is the connection between C infinity rings and derived manifolds. If I have an idempotent complete infinity category, finite limits, then functors from derived manifolds into C which preserve finite limits is equivalent to just C infinity ring objects in C. So, and also by definition, this is equivalent to functors out of manifolds into C which preserve transverse pullbacks in terminal object. So, So really, like it's just giving you like a very precise connection between the category of derived manifolds and that of C-infinity rings. And as a corollary, just by some abstract algebraic theories, with the theory of abstract algebraic theories, we get that the infinity category of derived manifolds, one presentation for it is the opposite of finitely presented homotopical C-infinity rings. And when I say finitely presented, it's homotopically finitely presented. So that is that they are compact objects in that infinity category. Okay. So that's, I mean, kind of surprising because I mean, you'd think that, you know, it's like only some small subset of these algebras is going to model something like a derived manifold, but it turns out that you can get all finally presented C-infinity rings that way. And the upshot is, if you want to do derived difference geometry, you just do algebraic geometry, but over DG C-infinity rings. But I mean, it's really a mixture of differential geometry and algebraic geometry. I mean, some of the arguments you deduce to manifolds are kind of like essentially reducing to affine schemes in some sense. But then you have to do some more complicated arguments using algebraic geometry and homological algebra. Okay, so that's all I want to say about kind of background of what derived differential geometry is about. Now I want to talk about some field theory stuff. Okay, so let's first start with classical field theory. So the ingredients we're going to have is we're going to start with, so I'm going to describe Lagrangian field theory. So we have space-time, we have some sort of bundle over space-time, and sections of that bundle is going to be a space of fields. Now, space-time is just a name if you're thinking mathematically, but in actual physics, I mean, you can take this to be like R4 with Lorentzian metric if you're non-curved space-time. And we have an action functional. So we have a function on the space of fields, but the function takes values in densities on the manifold. So if your manifold is oriented, that's just top forms. So something you can integrate over the manifold. And it should be local, so it's only going to be depend on finitely many derivatives of the field. Okay, so it's a function on, I think it was a function on the infinite jet bundle, if you will. In real life, it's usually only depending on like one or two derivatives, but that's just like the theory is general like this. Okay, so if you want to understand the dynamics of the field, well, it's given by the Euler-Lagrange equation. So it just says a variational derivative of this action is 0. And you can express this also as asking for, well, think about this as a variation of the Lagrangian density to be 0. You can make sense of this using the variational bicomplex. Okay, so it's just directly translating the variation of S being 0 in terms of the Lagrangian. Okay. So other questions so far? Okay. So now let's go over to the quantum world. So I'm going to add some Planck constant in there. So I'm going to go to quantum field theory. So in quantum field theory, we have some sort of algebra of quantum observables. So there are some sort of functions on the space of fields. And you want to be able to take, say, expectation values of these. So this is defined, except for the fact that Feynman integrals are mathematically defined in general, but it's defined as this, this Feynman integral over the space of all fields of the value of the operator on the field, and then you weight it with this exponentiation of the action functional. The way I wrote it right now is a Lorentzian signature, because I have this I, otherwise you have a -1 in Riemannian. It doesn't really matter, the theory is going to be the same. and then you just divide by what would happen if you had just the identity operator, and that's called the partition function. Okay, so this thing d phi is some sort of it's representing something which ought to be a measure on the space of fields, but it's typically infinite dimensional. So okay, I don't know what that says. There's a I don't read check. I'm sorry. There's a comment which I don't know how to answer. Okay, so let's look at this, but in the case we can actually do this. Okay, a warm-up example. Let's make space-time be a point. Okay, so then I can have a fiber bundle over the point is just a manifold. So now the space of fields is a manifold, it's finite dimensional, I can do something. And let's even just make life simpler. Let's assume it's a compact manifold that's oriented. So really there's no problem with integration. Okay, let's make it as easy as possible. Then the action functional is nothing complicated, it's just a smooth function on that manifold. Okay, before it's a bit more subtle of it's not technically a function. And I should mention also, if I go over here, this is a kind of formal expression because there's no reason that this integral would actually converge, and you just don't even care. You just write it down anyways. So it's kind of like, it's really the Lagrangian density you're studying in some sense. So, okay. So now let's just fix a volume form. So a nowhere vanishing top form, and this is a morally our d phi, or it actually is our d phi in this case, because this is like a very, very special case of this setup where you can actually make sense of it. So let's make an observation. If you contract with this volume form, you get an isomorphism between multi-vector fields and n minus I forms. Okay, and the Derived differential on forms, you can just transport it via these isomorphism, and you get a differential which is the divergence operator of this volume form. Okay, so actually I just realized I forgot to show you a piece of the presentation which is floating on the top right. So I think this is a good time to go back over that, because I'm going to need to connect with that. So I apologize for being slightly out of order, but this shouldn't confuse things. So let's just hold that thought. Right. So I want to do one example of a derived intersection. So I want to go back to this example of a moduli space that we had. So I have a vector bundle and I have a section. I want to compute the derived intersection of that section with the zero section. And you can do this using derived manifolds. First, you can talk about graded manifolds. So you can just shift the fiber of that vector bundle in a graded sense by one. And what this amounts to as a graded manifold is you have the same manifold as before as your base, but you have a structure sheaf now, which in degree minus n is sections of the nth exterior power of the dual of the vector bundle. Okay, this is literally just taking the fiber and shifting it. So if you have a graded vector space, there's a way of making a graded manifold out of it, just the way that if you have a vector space, there's a way of making a manifold out of it, right? If you have Rn, you get Rn as a manifold, and you can extend this functor to graded vector spaces and graded manifolds, and then make sense of a vector bundle, and then all the operations you have on graded vector spaces you can put to graded vector bundles. And so the shift operation makes perfect sense, and this is what it does. So this is really a geometric thing. And now you can put a vector field on this graded manifold, so it's a derivation of the structure sheaf. Inserting this section is a derivation of the structure sheaf, because we're using the exterior power of the dual. And well, if you insert it twice, you get 0. So it graded commutes with itself. So this gives us a DG algebra, and it's a DG C infinity ring. And so if you take smooth functions, this models the derived zero set. And one way of convincing yourself this does the right thing is if you look at the cohomology of this differential. If you take an open which does not intersect the zeros of the intersection, it's a cyclic. There's no cohomology. And all the cohomology is concentrated on the actual intersection of the section with the zero section. And moreover, if you happen to have transversality, then this algebra is quasi-isomorphic to just smooth functions on the actual intersection. So, and this just follows from, because this is really in local coordinates, it's just a causal resolution. So, okay. This is, so this is like a concrete thing you can do. All right, where were we? Okay. So, okay, so let's go back. So you can see that something like this is kind of slowly creeping up on us. We can look at the multi-vector fields, and then we get an isomorphism of chain complexes, or a quasi-isomorphism. It's actually an isomorphism in this case, an isomorphism of chain complexes between multi-vector fields and volume forms, sorry, not volume, differential forms, but I mean, they kind of go in the opposite direction in this sense, right? So we can identify. Yep.
This volume form that you're talking about,
yep.
It should be the analog, or it should be interpreted as the path integral measure.
Yeah, it's the path integral measure, exactly.
Right. Yeah. So what is the small n? Is it the dimension of something?
It's the small n, because I'm in finite dimensions right now. So it's a dimension of the fields.
Sorry.
Yeah.
Otherwise, because in infinite dimensions, there would be no, strictly speaking, top form.
Well, exactly. So first I'm doing a warm-up case of when it's finite dimensional. So, so you can also run this with a complex valued volume form, no problem. I mean, you can just tensor with C, right? So now let's look at what the expectation value is. So you want to look at this integral divided by the integral of just the volume form weighted by this exponentiation of the action functional. Okay, so let's follow through a series of isomorphisms to get that number out. So we can start with just smooth functions to the complex numbers, and well, that's smooth functions that's H0 of the differential forms, right? So that's oh, did I do the? Sorry, it's H0 of the divergence complex using multi-vector fields. And now I can identify that with Hn by multiplication, so by contraction with the volume form, okay? And Hn is the same thing as C, but the isomorphism is integration, right? So that means you can define the expectation value as just the image of x in cohomology divided by the image of 1 in cohomology, right? And that gives you an answer. And this doesn't, like, this n answer, that's saying in here. So like, this is always going to make sense once you have something playing the role of divergence. And we may not be able to identify it with C, but it certainly makes sense, and without having finite dimensions. Okay, so a simple calculation you can do, it just uses Cartan's magic formula. I made a stray mark, I'm trying to get rid of it. There we go. Is that you can compare the divergence operator when you weight with this expectation of the action functional with the one coming from the original measure, the original volume form, and it satisfies this this condition. Okay, and so this is the differential on multi-vector fields. Now you can set h bar going to 0, And you get that this divergence operator collapses to insertion with respect to ds. Okay? As a chain complex. And as a chain complex, it's a multi-vector fields. As a cochain complex, it's the same thing, but they're in degrees minus n, right? And that's just smooth functions on the shifted cotangent bundle, with the differential being insertion of ds. That's a model for the derived zero set of ds, as we saw, as a DG manifold. So we get the so-called derived critical locus of the action functional just popping up out of nowhere, seemingly. And this leads us to study the derived space of solutions to the Euler-Lagrange equations. Okay, so we see that already there's a connection between derived differential geometry and the path integral formalism of quantum field theory.
So can you run through that equivalence, the sequence of equivalences again? So the one that ends up at the
Which one?
locus?
Yeah.
So you're looking at the path integral, right? And then eventually you end up at the derived zero locus.
Right. So you start with the path integral. You want to make sense of you interpret it as taking cohomology in this divergence complex.
Right. So in the divergence complex, anything that's contracted with you know, the equations of motion is zero, right? That's the idea.
Yeah. Yeah.
Okay.
So and now you look what happens if you have the divergence operator with when you don't have an action, or you have the trivial action functional, right? So just to measure. And you'd have two different differentials you can put in the same. Exactly. And it satisfies this algebraic condition. So you see that with the H bar dependences. So if you get rid of H bar, you're left with a bare differential.
Mm-hmm.
So it's like kind of the semi-classical limit. So already semi-classically, you get this derived critical locus popping up.
Okay, so the connection is through the classical limit, H bar going to zero.
Yeah, exactly. So we,
okay, as would be expected.
Right. So that means we can like, right. So that's what. So if you want to quantize, you have to like undo the classical limit, but you can start with the derived thing. So you already start with the semi-classical thing.
Okay. Very good.
So. Okay. So let's go back to looking at this this nice equation here, which, like I said, it follows basically from a Cartan's magic formula. So suppose that H bar isn't zero. So now we're looking at the actual quantized thing. What do we get? Well, there's some more structure on this algebra. So you have a Schouten bracket of multi-vector fields. So that gives you a one-shifted Poisson structure. And we have this divergence operator. It's a derivation of the Poisson bracket, but it's not a derivation of the product. The product here is wedge product, but it's close to being. So what you have is, so if it was a derivation of the product, you would have this quality here. But what you actually have is you have to add the Poisson bracket. So, and actually, I think there should be an H bar there in front of the bracket VW, but there might be some H bars missing somewhere. I apologize. But this is, so in some sense, the Poisson bracket measures the failure of it to be a derivation, okay? And you can axiomatize this structure. There's some more properties that should satisfy, and you get something, if you keep track of H bar in there, something called a BD algebra, or a Bellingson-Drinfeld algebra. And it's a it's a deformation with parameter H bar of functions on the derived solutions of Euler-Lagrange equations. Okay, if you set H bar to zero, you just get back, contraction with ds as your differential, and it's a commutative algebra. So okay, so what do we do when I'm not in finite dimensions? So I actually have a space-time which is positive dimensional, which makes fields immediately infinite dimensional. So let's go back to here. So now we have the space of fields. I have my action functional, and I can think about the Lagrangian density as being a smooth function with values and densities of the manifold. And you want to take whatever the derived space of solutions or Lagrange equations is. But what do we mean by that? Okay, so here's the idea. So in the case when finite dimensions, I have my Lagrangian is just say a smooth function from like values in R. I can take the differential as a section of the cotangent bundle, and they can take the derived intersection as a critical locus. That's easy. But now we don't have a real valued smooth function anymore. We have a density valued function. So you want to have an analog of the cotangent bundle. We call it the variational cotangent bundle. So this is work of mine with Owen Gwilliam. So we set up this formalism. And so we have to be really careful because this is also infinite dimensional, okay? So we want to develop something which is like takes over the role of the cotangent bundle, and it works in infinite dimensions. And we want to be able to interpret the variational derivative of the Lagrangian as a section of that in such a way that its derived intersection with the zero section is the space of solutions, the Lagrange equations, okay? So that's kind of the idea. And before we go into this in the derived way, there's already another issue because we also have something I didn't talk about at all is gauge symmetries, okay? So you might have redundant information in the space of fields. You can have two different field configurations which actually are representing the same physical physics because they're related by a gauge transformation, right? So in general, we have a gauge group acting on the fields, and you have the same physical system described by two different fields when they're related by an element of the gauge group. And the main example comes from just classical gauge theory. So we have the starting data of a principal G bundle. Usually it's just a trivial one, but you can do this for an arbitrary one. And then we have the affine bundle of connections, which is just the tensor of the cotangent bundle with G if it's trivial, but in general you have an affine bundle. And so the space of fields is sections of that, so it's just connections on the principal bundle. And then we have so if in the trivial case, smooth functions into G is the gauge group, and more generally it's actually a bundle of Lie groups, which is sections of the adjoint bundle. So we have to take this into account. So we get the derived space solutions in two steps. First, we take the fields and we take a Stacky quotient. I didn't say where though, but this is just the idea, right? And then we take the variational cotangent bundle of the Stacky quotient, and this inside this bundle, it contains information about ghost fields, like in the BRST sense. So it takes care of the resolution in terms of Lie algebra cohomology and the anti-field at the same time. Okay, so how do we formalize this? So a formal setup is we work with sheaves over, well, basically when you sheaves over derived manifolds, and this would be like a place where we can work. But we're going to actually thicken it a little bit just to make life easier. So we have infinitesimal algebras around. And then we can make sense of the space of fields just by its functor of points. So now D doesn't have to be a manifold. D could be a derived manifold, right? And like the maps from that into the space of fields is just D-parameterized sections, okay? So like if you were actually working with ordinary manifolds and you did this, you would actually get, and say that you were looking at, say the fibers were compact, then this would literally be the fresh, like functor point to the Frechet manifold of sections. I guess maybe M should be compact in that case, but. So we can make sense of TF just abstractly in this setting. Okay, so we can take its tangent complex, for example. The tangent complex over a field, that's just going to be, well, it's actually just going to be a vector bundle. It's going to be sections of a vector bundle. It's just sections of the pullback of the vertical bundle of the configuration bundle. Not surprising, but it literally comes out to that, like, abstractly. So that's like, you know, that's good. And we want to be able to talk about what the variational cotangent bundle is. So now to do this, instead of taking, so we want to take the dual, but not with respect to R, but with respect to densities, because we're taking density valued functions, right? So this is accomplished by the so-called Sear dual. So you take, you pull back the density bundle, and then you tensor with the dual. Okay, it's a relative Sear dual respect to the bundle. So and what it has is literally, it's the value at a field is just sections of the dual tensored with densities. Okay, so our variational cotangent bundle is just sections of this Sear dual. Okay, and this actually does the right thing. It gives you exactly the right anti-fields you'd expect from, like, they say, the BV point of view. And so now we can look at what happens when you take the stack equotient. So the tangent complex, so this is a 2-vector bundle now because we have a stack. So we have actually a complex instead of a vector of a tangent space, the 2-term complex. And just by abstract theory, this is just the Lie algebra of the gauge groupoid mapping by the infinitesimal action to the tangent space. And you can interpret this map in terms of the infinite jet comonad and the de Rham stack. If you don't know what that means, that's okay. But, like, maybe that's kind of throwing that out to Igor, because he likes these things. But this map is always a differential operator, okay? It's always a differential operator, and it makes sense to take the formal adjoint, okay? So we have this formal adjoint of this differential operator, and this we can interpret in terms of Verdia duality, okay? So we can understand the formal dual as just being implementation of Verdia duality, and we can make sense of the fiberwise Verdia dual of the tangent bundle. So this is something which you can just do abstractly, and that's what we call the variational cotangent bundle, okay? And it's literally doing, so it turns out to do exactly what you want to do in the BV setting. So I'll say that in a second, but once you have this, you can now just take the homotopy equalizer of the 0 section and the variational derivative, and you say that's derived critical locus. It's 9 now. Okay, I have about 5 minutes. Is that okay?
Yeah, that's fine.
Okay. All right, because I want to say what actually happens here. So okay, so here's kind of what's going on geometrically. You have like the derived critical locus. And you can take one particular field, and now we can look at the formal neighborhood. So the formal neighborhood is encoded by an L-infinity algebra. This is general phenomena. So formal neighborhoods are, so formal moduli problems are the same as L-infinity algebras. And the underlying infinity algebra, the L-infinity algebra is the tangent complex. And you can do some calculations. So for example, in 3D Chern-Simons, you get literally the, if you do this whole construction, you get the differential forms with values in the adjoint bundle, where the differential is given by the covariant derivative, which is a differential precisely because it's a flat connection, which is so it's a solution to Euler's grounds equation. So that's very satisfying, and that's actually exactly what you expect from the BV perspective. And you can also do Yang-Mills, which is more interesting because you have a gauge group. Actually, they both have gauge groups. I'm sorry. you can just do Yang-Mills, and more interesting because it's physical. And you get essentially the same thing, except for here you have this star, Hod star operation. So, and that's also exactly what you expect from BV. So this is like, for instance, in the work of Costello and Gwilliam. Okay, so what do you do with this? So if I have a formal moduli problem, which you get out of this derived critical locus, you look at this L-infinity algebra. You can look at Chevrolet-Allenberg cochains, and it gives you some factorization algebra with values in P0 algebras. So this is, and this is basically what would happen, like, it's your semi-classical limit. So this is what you had way before when we set H bar to 0, when you had this Poisson algebra. And you can input it as a machine of BV-quantization, and if you pick a quantization, it spits out a factorization algebra with values in BD algebras. You can forget about this whole factorization algebra part for now. You're just like trying to find a BV Laplacian, something playing the role of divergence with respect to mu H bar as before, okay? And then when you set H bar to 0, you get the old thing, right? So this is one way of interpreting BV quantization. And I guess what I wanted to end with is that you can do something deeper. You can do this in families now. If I have any map from any derived stack into the derived critical locus, in particular, I could take the identity map. So I could do it on, so like the universal family is just the identity map, the map from derived critical locus to itself. And you formally complete, you get a sheaf of L-infinity algebroids over X. So this is due to work of Newton. So instead of taking a point and getting an L-infinity algebra, you get an L-infinity algebroid. But you can still take Chevrolet-Allenberg cochains and plug it in, and it makes sense to look for a BV quantization. So this is a lift of this Poisson algebra structure to a BD algebra. So this leads you to study global BV quantization. So that's something which I'm hoping to develop together with Owen Gwilliam and perhaps some others. Okay, so that's all I want to say. Thank you for your indulgence.
Okay, awesome. Let's everybody unmute ourselves and thank our speaker. Okay, so I'll open up the floor. Are there any questions? Yeah,
So
just unmute yourself and go for it.
I'll start with maybe a general comment.
Yeah.
So the steps that you went through to arrive at the BV formalism as some Chevalier-Allenberg cochain construction on in the realm of DG algebras. So I mean, I think that's familiar to people who study this stuff. And I think if you restrict yourself to the situation where all these, the solutions space of the Euler-Lagrange equations can be described as a normal classical manifold, then like this derived differential geometry business doesn't come in at all, and this it's kind of a standard story. But perhaps one could interpret what you have told us is that the same steps that people usually use in that situation, they have some analog in this much more complicated derived differential geometry, derived manifold category. And so you can do all the same steps, interpret it in the correct way, and you get something which is meaningful in this derived manifold category. Is that right?
That's true, but I mean, if you take any gauge theory, you're going to have to do this derived stuff, because your Hessian's always going to be degenerate, right?
Well, it depends what you mean. I mean, if your gauge symmetries are such that when you take the quotient with respect to the gauge symmetries, you don't leave the realm of classical differential geometry. Then you just work on the quotient, right? So everything is just designed to get you down to that quotient. I'm not saying that that's the only thing that you should do, but you could.
So, I mean, I guess what I'm thinking more like upstairs if you're trying to do the Feynman path integral. And so, I mean, the way that like you're really kind of using some sort of a stationary phase approximation, right?
Mm-hmm.
So you need the Hessian to be non-degenerate in order for this expansion to work in terms of Feynman diagrams. Mm-hmm. And if it's not, you don't get sensible answers. And so if you have a gauge symmetry, like almost all the time, you don't get a non-degenerate Hessian, so you get a degenerate one. You have to do something. That's why, like for instance, even BRST was invented, right?
Yes.
So this does that automatically. So like BRST is basically the formal neighborhood version of what we're doing.
Yeah. Okay. I understand. So in that sense, you're saying that you start with some kind of overarching universal principles, and then the BV-BRST construction kind of comes out naturally out of that.
Yeah, it comes out as it's the formal neighborhood. So we have a big global object, and if you just look at the formal neighborhoods, you recover this BV stuff, like at least semi-classically, right? And this thing I was calling global BV-quantization, which like at least can say what it is, but not how to do it, is a way of like doing BV-quantization coherently in families. So it would be something which is like better than what we're currently doing, so to say, but it will recover it in the case that you just have a point. So have one solution.
So basically you're saying that the contrast you're drawing is between like picking some background classical solution and doing perturbation theory around that, compared to do the perturbation theory around every possible classical solution and consider it as one global object. Okay.
Yeah, exactly. Or you can do any family of solutions. So it doesn't have to be the whole of them, but like anything you want.
Let's imagine that we live in such a perfect world that there's some example where all of what you just said can be done without invoking derived manifolds. For the reason, as I said, that you can, when you do quotients and intersections, you only get classical manifolds. Right? Then maybe somebody came up with a BV construction, but just as a kind of intermediate step, and one ends up with a classical geometric object in the end. So my question to you now is, suppose that you want to convince somebody that your framework is kind of interesting by giving some example where you are obliged to leave the world of the classical geometry, right? So what would be kind of the first non-trivial example where you're forced to go to the this derived manifold picture to describe some particular example that you might be interested in?
Well, it depends who the person is. If they're a physicist, you can just say, well, Yang-Mills is going to force you right away. So, I mean, it's certainly not
for what reason?
The simple.
You're still talking about the degeneracy of the Hessian of the Lagrangian?
Yes.
Right, but notice that I said that in principle you can do the path integral after doing the quotient by the gauge symmetries. I mean, I'm not saying it's going to be pretty, but you can do it. Okay, so then you're not forced to go to the derived manifolds in that case. But is there another example where you really are forced, where you can't just do the gauge symmetry quotient first and then do the path integral? Or
if you just write down the Lagrangian, chances are that like even if there's no gauge symmetries, chances are that like if you look at the variational derivative, it's not going to be transverse to the zero section. I mean, unless it's like
can you make that concrete? I know you can say that almost any function that you write down, any continuous function is not going to be differentiable, but right? It's nice to give an example and say, okay, here's a function that's not differentiable. So if you're
no, it's differentiable. What no,
I'm just giving an analogy,
gun to my head, I'm going to be like, come back later, like, please don't shoot me.
Okay.
No, because I just have to, like, I have to play with the actual, like, I haven't done so many calculations yet. I've worked really hard just to do these ones.
Okay.
Like, because I'm still in the process of, like, writing down all the intricacies of the theory, so to say. So, like, basically, if you ask me a month later, I probably have a whole bunch of examples because I will be including them in my paper. Yeah, but like I have to run some of them first and see what comes out.
So maybe I could guess that if you're dealing with some field theory where the Euler-Lagrange equations define a solution space that has singularities like conical points or some other kind of then that would be a situation where you're forced to
absolutely
to use these tools. Okay.
Absolutely, yeah. I mean, like anything which is like, I mean, if you have even just like what phi squared in there, then I mean, let's see.
You mean like phi squared equals 0? That's a kind of equation.
Yeah, exactly. Like I mean, because it's gonna be if you that's like, you know, a parabola with just a line like this, right? It's not transverse. So that's already not going to work.
Right. So I can actually give you a more interesting example. If you consider general relativity or Yang-Mills theory defined on a manifold with a compact Cauchy surface, then we know that the solution space of those theories has conical singularities around configurations with extra symmetry. So if there's any extra global symmetries around particular configurations, we know that they are conical singularities in the solution space. So I think that's a good example. People kind of like sweep it under the rug most of the time, and then one thing that you can say is that they don't have to sweep it under the rug using this derived manifold.
Yeah.
Okay.
And like as you see, you get like, sure. And like you get sensible things out of this construction, not just kind of like gibberish, like not some abstract stuff. Like you get something tangible, which is what I like here. So,
do we have any other questions?
I have a couple.
Okay, go for it.
The first is the infinity category C infinity, and the one of differential, the derived differentiable manifolds. Are there pre-geometry and geometry in Lurie's sense? I think now he changed the terminology, but
yeah. So yeah, exactly. So like, I mean, if you're comfortable with that language, yes, you can write down a pre-geometry or even you can even write down a geometry for finally presented C infinity algebras, right? So you let your G be finally presented C infinity algebras, I guess, up, because you want to do pro of that, right? So yes, then you can write down the geometry, and your admissible morphisms are going to be localizations with respect to a set of elements such that the ideal that they generated, so the ideals don't have to be the unit ideal, but if you the germ determined ideal that they generate. So like if you extend it by like saying if you are in there like germ wise, that gives you the identity, and that actually corresponds exactly to this is a spec functor. There's a spec functor which you can write down without using Lurie's formalism. You can just write down like a very geometric spec functor. Or you can even get it by using the universal property of derived manifolds, and this like you have the functor topological spaces, and then you you can extend it, and that's just open coverings of these. It's just open covers of these geometric schemes. Yep. And so yeah, it does fall into that framework.
Thanks. And the other one, I think I missed where you performed the actual Stecky quotient with respect to the gauge group.
Where I did it. So what do you mean concretely? Like,
I've seen an infinity topos at a certain point, and is it there
Yeah.
that you?
Oh, yeah. So first I told you what I was going to do, and then I just like, because I said take the Stacky quotient and then do this variational cotangent bundle, and so then I just I did it over here.
Right, exactly. I missed precisely that point.
Okay, yeah. So first I did it without a gauge group, just so you had an idea what the variational cotangent bundle was like in the simpler case, right? And then I just like then I said what happens. Well, so you take what the variational cotangent space at a point and is the formal adjoint of this covariant derivative operator, and that actually turns out to be the same as the covariant derivative operator on the dual.
I see.
So yeah, so like that you can kind of see that in the and these two pieces, like these are essentially the same complexes except for this Hodge star part, right?
Mm-hmm.
So like this two-term complex and the last two-term complex are what come out of the variational cotangent bundle and the variational, and then just the tangent bundle, and then this connecting piece exactly comes from the variational derivative of the action. It was what glues them together.
Okay, thanks.
Yep.
Okay, if there are any other questions, now's the time. No, otherwise let's thank our speaker again.
Thank you.